So this is section 9.6, part 3, and we're looking at this series right here. And so the fun thing we're going to do right now is look at why none of the tests that we know so far work. So first of all, let's say we look at the nth term test. So I want to look at the nth term test. Well, do I really know what the limit as n approaches infinity of this is? I can find it out. And the idea will be to eliminate if maybe this is a divergent series. Now, by the way, I suspect it is convergent because the denominator is exponential. The numerator is just a polynomial. So I think that the exponential is going to grow faster than the polynomial. But that's not a justification. What I need to do for the nth term test is look at the limit as n approaches infinity of n cubed over 3 to the n. So, but it's hard to say what that is. But there is something we can do. Since the limits of sequences follow the same rules as the limits for functions, really what I'm about to do, imagine that we create a function that is a real valued function. The domain is real values. This domain is natural numbers. And in that case, whatever the limit of that real valued function is the same as the limit of the sequence. So what that enables me to do is do what I can't do with just a sequence, which is take a derivative and use L'Hopital's rule. So if I use L'Hopital's rule, this is limit as n approaches infinity of 3n squared over 3 to the n ln 3. I've observed, by the way, that this is an infinity over infinity form. Now what I get here is still an infinity over infinity form. The numerator is going to infinity, denominator is going to infinity because of the 3 to the n. So this equals limit as n approaches infinity of 6n over 3 to the n ln 3 squared. So I'm just doing L'Hopital again. I just keep doing L'Hopital. I'm doing derivative of top and the bottom. It's not a quotient rule. It's L'Hopital's rule. So I have limit as n approaches infinity. I'm just doing the derivative of the top is 6. Derivative of the bottom. I'm going to pick up another ln 3 term. So I have 3 to the n ln 3 cubed. Now at this point, I can determine that the numerator is bounded, the denominator expands without bound, so that limit equals 0. But here's the thing about the nth term test. The fact that the limit of the sequences equals 0 tells me nothing because I don't have an alternating series. It's not alternating series test. All this tells me is I don't know for a fact that it doesn't diverge. So I have no conclusion there. From nth term test gives you no conclusion when the limit of the sequences is 0. Next thing I might consider is the integral test. So do I want to do the integral test? Well, for integral test, I need a sub n positive, which I know it is. The other thing I would need is a sub n decreasing. Well, it's not entirely obvious that this function is decreasing. Now, I won't go through this one. You can show that this function is decreasing, at least for n greater than or equal to 3, by finding the derivative of this function, this sequence as a function. So consider the function x cubed over 3 to the x. You find the derivative of that function using the quotient rule this time, not L'Hopital's rule, but using the quotient rule. And what you're going to find is you get something that is always negative, or at least it's negative once n is greater than or equal to 3. You can try that if you want, but it turns out that, yeah, it is decreasing, and a sub n is greater than 0, but proving that this decreases so that we can apply the test is not easy and not something that we necessarily want to do. And then the other question we would have is, do I really want to do the integral from 1 to infinity of x cubed over 3 to the x dx? Now that's doable because I can write it as integral 1 to infinity of x cubed times 3 to the negative x dx. And then this is integration by parts, and I can do parts 3 times and get what that, and then apply a limit to it and get that integral. All right, I could do that, but it's a little daunting. That I'm going to look at that and say, you actually can do it this way. We can prove that this series converges using the integral test, but it's definitely the hardest way to do it that you could do. Okay, let's try a comparison test. Can I compare this to a known divergent series? Like compare it to, just using parts of what we have there. What we're really looking at here is different strategies we could employ. None of these are full justifications. They're just strategies, kind of thinking out loud. So could I compare it to the sum of n cubed? Well, because I know that diverges by nth term test. But the problem that I have is that my terms, n cubed over 3 to the n, they are less than n cubed, because I'm going to take my n cubed and divide by 3 to the n. I'm going to get something smaller. So I have this situation where I have my problem series is less than a divergent series, tells me nothing. There's no conclusion. let's try comparing to sum of 1 over 3 to the n, because that is a geometric series with r less than 1. So it's geometric series, absolute value of r, which is 1/3, is less than 1, so it converges. All right, but how would my comparison go? How would I compare n cubed over 3 to the n to just 1 over 3 to the n? How would that compare? Well, the n cubed term is bigger than the n cubed. So what I end up with is my problem series is greater than a convergent series, which again tells me nothing. So I have nothing again. All right, well, these are the situations where I want to try and use limit comparison test. So limit comparison test. Limit comparison test says, I can compare. I think my most productive comparison was 1 over 3 to the n, sort of captures the geometric nature of, or the exponential geometric nature of this, which is probably the dominant feature of this series. So it sounds promising. We're going to look at the limit as n approaches infinity of a sub n over b sub n. And a convenient way to write that a lot of the times is going to be limit as n approaches infinity of a sub n times 1 over b to the n, because b sub n, because since each a sub n and b sub n are fractions, this fraction becomes unwieldy. So we'll look at what that limit is. And again, we'll use our a sub n is our problem series, and for b sub n we'll use the geometric series again, just see what it looks like. So if I do the limit as n approaches infinity of a sub n times 1 over b sub n, so that's going to be n cubed over 3 to the n times, so for the 1 over b to the n, I just take the b to the n and flip it over, 3 to the n over 1. So that looks promising because the 3 to the n's cancel out. I have limit as n approaches infinity of n cubed. But that increases without bounds, so that's just infinity. That's the one thing I can't have with a limit comparison test. If you want to write it, this is not an element of the interval 0 to infinity. So once again, I get no conclusion. So far, I've gotten no conclusion from any of my tests. Is there a test, I say? Is there a test that will prove that this series converges? There is, and that is the subject of our next video.